Good morning. We're getting started 2 minutes after 8. There's just 4 people in class. One person said he wasn't coming in because of snow. I'm not sure that anybody got that much snow even up in the Black Forest, but you know, if you don't have the right vehicle, I guess it's hard. I live just east of here on a very steep hill that goes up to the top of the bluff that looks down to the south at Palmer Park. So that's where I live, and my bike would have not made it down without wiping out because it was very icy this morning on a north-facing hill where the sun doesn't shine this time of the year. So I took advantage of the parking that the chancellor provided for all of us. I just wasn't going to do that if I didn't have to, but I decided for a little bit of nostalgia's sake, I would go park in front of the library that I always used to do for years and years when I felt like buying parking gave me a return on my investment. You know, years ago I decided it doesn't give me a return on my investment. That's why I bought the e-bike. At any rate, I pushed the papers back to you this morning, and I was saying just before I started the recording that the papers are just really, really hard for me to get through. If they're well worked, they're a breeze and they're pleasant. When they're not worked well and people take left and right wrong turns, it's very frustrating. And then many of you, and this is a sad commentary, I believe from what I could tell from seeing commonalities in papers, you're out there looking for, scavenging for solutions. That is just, I'm just so angry when I see that happen. It's like, don't do that. Don't use Chegg, don't use anything. It is just an unethical type of behavior. You have to do your own work. You just have to, you learn the material and work at it. When you do a bunch of nonsensical stuff that you find somewhere, it's like, no, this is crap. And I've seen that my entire career, and I see it again. I mean, you're saying, yeah, Dr. Wickert, you're complaining to us, you're giving us the up and down treatment, but it's just bad behavior. You can't do that on the job. You got to do your work. And that kind of thing just irritates me to no end. So try to refrain, try to resist the temptations in your body, physical, to go searching for junk. Just do the work as it's assigned from the book, from the notes, and the other hints that I provide. Another thing that, of course, aggravated me during Thanksgiving, and I'm sorry, but I just had to take some time away. My family was saying, what are you doing? You shouldn't be doing the grading papers even, which I tried to do, is people not reading the materials I've given you. I've told you that there are hints in the notebook that I put up there. There's more of that in the last 2 homework assignments. So just take the time to sit down and read. Don't be a simple, silly consumer that says, I want it handed to me right in my face. But you have to do a little bit of digging to get stuff, but do it. Just do the work. Don't slough off like that. And yes, I have some syntactical errors because my partner, Charanth, changed syntax a year ago, and in some cases I haven't fixed everything. In some of the writing, most of the notebooks, it's all fixed in though. In the Julian notebook that you had to run had something that didn't work originally as defined, but you know, I did patch that up, I think, on Sunday, but still not really big issues. Those were optional things that I'll see when I grade the project. And the first project, yes, it's a lot of work. It's a huge amount of work for me to grade. I anticipate spending at least an hour going through each project, which, because only one pair of you worked as a team, I definitely have a lot of grading to do because almost everybody turned in their own project. Now, if you're a graduate student, you had to turn in your own project. But consider teaming up for the second project, which is a totally different animal. It's much, much easier to work. We'll look at it today. We're going to get into that pretty quickly. But first, I want to go through the synopsis of things. And it is a very busy time of the year. All the graduate students and the senior student who's doing a research project, everything comes to a head right now. So I've got 4 people that are doing activities that are rolling out. The first one is this Friday at the Mountain Lion Research Day, and my student working on that still hasn't given me his slides to look at. Then I have 3 more graduate students that have scheduled dissertation or thesis or master's project defenses. So I'm staying busy, probably beyond the end. I'm not happy with that, but it's getting out of here is kind of is my big thrust right now. But that doesn't mean I'm stopping with the material, so the show goes on. So last week, I think over the weekend when I finished grading the homeworks, I put up a set of histograms, and then yesterday I finalized the histograms when I finished grading exam 2. So we're going to take a quick look at those right here. So this histogram just tells you what the scores were on sets, or this document with the histograms coming up at the end shows you what happened on set number 4, what happened on set number 5. 3 people didn't turn it in, but I still had to enter zeros in there just so I could combine it with the other score sets that I have. And then this is what happened on set number 6. In all cases, people were getting the bonus points. I think pretty much in every case, over 100% of the points were obtained by at least one person. So these are the histograms, though, just showing you what happened on set number 4, set number 5, and set number 6. And then probably the most important thing is I pooled together sets 1 through 6 to form a composite histogram. And you can see here, and this is probably the most important thing. If you don't want to look at the other ones, they're just there so you can have that data if you like it. But this one tells more of a story because it tells where we're at right now with the homework. The mean is 83, which is not too bad, but it's kind of counterbalanced by the fact that one person has over 100% and one person has just over 60% composite score out of 6 assignments. But I can work with it. This is not out of the ordinary for me to see something like that, and 2 people are in the 90s. So homework, about right. I'm giving partial credit. I'm not zapping you if it looks like you copied something, but I'm not giving you full credit. And you know, another pet peeve I have is some of you like to be very minimalistic and cram all your work into a little piece of paper that makes it really, really hard for me to grade on. At the very beginning of the semester, I said put each problem on a new page. That would be very much appreciated, but at least put a space in it. There's one person that writes every line of the notebook paper, and it's just like so compacted. What can I do? I see a bunch of gibberish and I can't figure it out, and then I want to comment on it and I don't have any space to write. So please see if you can prove yourselves better and spread things out a little bit more so I have space to write. You have 2 assignments to turn in. They're going to be relatively easy compared to the past assignments. But at any rate, enough said about that. Okay, and this is what I was able to do once I had the exam 2 graded. So the exam 2 scores are there. They range from 42 to 100 is the highest score. I then took and composited those scores in with exam 1 at 15%, exam 2 at 15%, and the current homework standing at 25%, and then divided by that fraction, the sum of 0.25 plus 0.15 plus 0.15. So I could have a basis of 100. So that gives me this bottom histogram. The top histogram just shows you the spread of the exam scores. And this being a take-home exam, generally the averages are higher because you have a chance to work on it in a more leisurely setting than here in the classroom. The composite, though, is what is probably the most interesting thing that you would like to have me comment on. So yes, one person will get an A if I had to give the grades today. That's pretty obvious. The fact that we have lower scores, I mean, I would hope that some of these bars would start pushing upwards. I don't know what the project is going to bring, but the project could be worth as much as 20% depending upon how you optimize your work on the final exam. If you remember, the final is worth, I think it's, I have to go back to the spreadsheet, or actually the syllabus. I did bring in a copy of the spreadsheet so I can tell you the numbers, so when that time comes. So I don't have that written down here, but I can go look at the syllabus again too.
25 or 30.
Yeah, 25. I was thinking, that's what I was thinking. Okay, so the final could count 30, and then the project grades combined together, project 1 and project 2 would count 15%. But if you don't do as well on the exam and you do better on your combined projects grade, then I'll let the project count 20% and the final only counts 25%. So there's a teeter-totter in there, and I use a max operator in my Excel spreadsheet to say compute the grade 2 different ways, whichever one is the highest is the one you get. So the projects are important. Project 2 won't be worth as many points as project 1. You can see what those ratios are like because at the back of each of the project reader documents I have I don't know if you've noticed, at the very last page has a grading rubric. Does anybody notice that at the end? So that tells you how many points. Now one thing I'm going to do though, and this you could be excited about, if the scores on project 1 are looking pretty sad, and you know, a year ago I had people that bailed out on certain parts of the project, I decided to not simply add those 2 scores together as raw numbers and have a project-based score. Instead, I did something like 40% for project 1 and 60% for project 2. So it would come together to make a total of 100. I decided to ratio it slightly just because of what I saw happening. Because I haven't started to grade the projects, but because I know what people have told me while they were pushing hard over the weekend with their Pi audio issues or other questions, and that makes me upset again too. It's like, why did you put this off? I gave it to you over a month ago. The idea was when you see you've got to have a hardware interface working, you go test it like immediately so we can work those bugs out. But no, procrastinators always wait to the end, and then when it blows up. Has anybody learned anything from this? Like, don't procrastinate to the end, especially when you have to get tools working. You can't do that in your life as an engineer. You got to be on top of it. I go test out my tools every time I have to put a patch or an update on, and I put updates on all the time because they come at me. So you got to make sure things keep working, because frequently they do break when you have an upgrade. So what I would do with the rest of these scores, I don't know. Because I have a really low score right now, composite average of under 60, if that individual can make it up to get even a D is going to be questionable. But, you know, I'm a person that has been teaching for many years, and I look at these histograms a lot. This is a statistical matter, and what always happens in a histogram of grade distribution like this is 2 things. Number 1, it tends to cluster tighter as more numbers come into play, and maybe that's the central limit theorem. You've all had prob and stats. Remember what that says? It tends to a Gaussian shape. It doesn't say it's going to become a tighter variance, but it tends to cluster more, and it tends to shift up higher as we get towards the end. So I expect that to happen, but by how much I can't say until I see it happen. But I'm convinced that it probably will happen unless people quit working altogether. Any questions on this discussion? It is only a grade, and the grade is not the thing that's the end all. It's the knowledge you gain and how you can use it in your work. But this is the system that we work in, and this is how I have to work with it. Any questions? I'm going to go up to the lab when we get done with lecture today to see what's going on in the lab with Chiranth. But I will have, I've got my Excel page here. You can't see it by looking at it from a distance, but it's two sides. So it's got the individual scores for each of the assignments, and then as I go across to the end, I've got two columns, which are the homework average, as I have it right now, and the composite, the one that's represented by this guy, if you want to see where you're at. Okay, so I'm going to move off of that. And if you don't like how kind of forceful I'm sounding, this is the last time I'm going to do this, but have I ever had to do this in my life before? What do you think, statistically speaking? Yes, it's happened before. I'll just tell you a little side story. I used to give both exams in class, and a really bizarre thing happened on exam 2 in this class one fall. I had one student that went out to go to the bathroom multiple times, and I'm like, this is starting to get strange. Why is this person going out to the bathroom, and why is this person gone for so long? I got really suspicious that something bizarre was happening. And a friend of mine, a graduate student, was the monitor in one of the CS department computer labs over here. And I said, did you see a student come in that you normally don't see? And you know, web browsers track your history, right? So he locked down all the computers, and he found out a student from my class was stopping off in the lab to go use the internet to go look at some of my solutions to homeworks and things on his way back from the bathroom. I prosecuted that case. I got the confession. The student got a 0. I could have probably dropped him from the exam, but then that went into his file. So yeah, that's a more bizarre one. I mean, I've had other crazy things, but that was like, why did I even think about that? But it's very unusual that most of you, unless you're sick, would be going to the bathroom that many times during an exam. So I'm going to get my water. I always remember that, though, because when I look in my files for this course, I have a special folder that has the records of what transpired as a result of that. And I have had other cases. I think every faculty member does, though, unfortunately. Okay, things I would like to do now. The good news about the material that remains, there's 2 topics, 2 chapters, but the material is not all that intense. It's very useful stuff, but it's not that intense, and the homework problems are not too many, and I have bonus problems everywhere. Things are pretty straightforward. It's just to kind of let you get practiced up, so when you come in and take the final, which will be cumulative, but will emphasize these last couple of chapters, you can be prepared. And the final will be here in class. It will be open book, open notes. So the next thing to move into is the project. I'd like to at least talk about that for a little bit. And I know some of you have started on it already. And yes, I could go through all of this, but I think unless somebody has a question on a specific problem, and I know I just pushed your papers back before I left my home today, I don't really want to spend time on this. I can let you look at it. Since somebody got a 100 points, none of you can doubt that the problems weren't workable, right? Somebody got 100, and that paper was very easy for me to work through as well. But that is here. This is the topic of chapter 6, structures. So that should kind of sound like, oh, this is maybe not as much math, and that's true. But I do want to talk about this project number 2 and emphasize a few details about it. It is, it is a pretty fun project. See if I can get this to work. If you're an undergraduate taking this class, based on the panicking I was seeing just the last few days, work in a team of two if you're up to it and want to coordinate, because that's the way engineers frequently work anyway. One of the reasons why we have projects in our courses is because our accreditation board wants us to do that sort of thing. They want to see people working in teams. Capstone Design does it, but it happens at times in other courses. So I can't force you to do it, and of course if you're taking it as a graduate student, you can't do it as a team. Right now I've given a little bit of slack in spite of having a lot of stuff going on. I'm giving you some time after the final. The final will be on Wednesday. I'm giving you until noon on Thursday, December 15th of finals week. So that pushes us down to this date over here. And I'm going to start at the back just because I have a lot of the code listing. There's a large module of code that's in the appendix, and it's called the GPS function module. It has functions and it has a class, a couple of classes in it, Python classes that make all of this stuff work. And yeah, the rubric is at the bottom of all of this too, if I remember right. I saw it. There's even 10 bonus points available on here. If you're taking control systems, the bonus points are more for somebody that's been taking control systems. But, you know, if you ask me some questions, I can point you at things too. Okay, so back up to where I was. I want to start by talking about, well, the fact that there's only 3 problems in here, and I'll back up to that in a second, but just say that after I created this project, I then went on to, let's see, I think I have to have, yeah, I'm supposed to be able to link on this, but the links were working at home, but now that I'm running the video, something's not working right with that link. But I'm going to go take a look at that link over here in the web browser, and that will just show you sort of what is the limit of all of this in terms of where this goes to. So I'm going to open it up in here, and then I'm going to go to the end and just follow that link. So after I did this project, and this project is geared towards signal processing, communications, and controls, I went on and had to do a short tutorial lecture for a company I was working at, and this is a derivative of that. It is something that Chiranth, those of you taking the lab know who he is. I was working for the company he was working for, and he put all this stuff up on GitHub. So he calls the project GPS Helper. So in the end, let's see where we're going with the GPS project. This is a 3-dimensional picture of what is going on when you're sitting on the ground. And in this example that I'm going to show you, that red dot is Colorado Springs. It's actually down by Cosmic AES's office, which is at Galleon Powers. So that's where I did my fictitious study that I'm going to show you here shortly. And it was done at a particular time of the day, particular month. I think it was January of the year that this was pushed up there. So I had what are called 2-line element sets that I obtained from the internet in order to get the current two-line element sets, also known as TLEs, for GPS satellites. I'm trying to think of the name of the site that I got them from. Track something or another. I can't remember the name of it. I mean, it's one that we always used when I worked at Cosmic. So I got the two-line element sets, and then I used a package in Python, which is also available in MATLAB and other languages, called SGP4, and it's a satellite propagating toolkit. And it's utilized in the notebooks that are up here on this GitHub site. So the 4 arcs that you see there represent the 4 satellites that I was tracking with my backpacking GPS that morning sometime in January. I knew exactly what satellites they were in the constellation of satellites because my GPS displays what satellite I'm locked onto. And the satellites in the GPS system are given a notation of SV some number. SV stands for Space Vehicle. So these were Space Vehicle 15713 or something like that. Whatever. I think this document tells you exactly what the satellites were. But so then I proceeded to do an experiment over a short period of time where I was tracking my movement on the ground using a local coordinate system called east-north-up. And I talked about that a few weeks back. It's a right-handed system, which means what? Think back to physics. What is a right-handed system? You have to hold out your right hand, and you use, think of how you cross X into Y to get Z. So east would be, if that's east, north is that way. So east, north, and then up is going to be up into space in the coordinate system I was using for the user sitting on the ground in Colorado Springs. And while I was having this user run around on a course, those satellites were also in motion because the GPS satellites are medium Earth orbit satellites. They're not geostationary, which means that they're moving. They're changing with time. So those little arcs you see is the amount of motion that the satellites took in their orbits while I was collecting the data. So this tells you about how to install it, but the most important thing for us is read the docs. So this is the read the docs that I want to go to. I thought I went to this. Okay, did it say read the docs was down? I think it did, which is kind of unfortunate. So maybe I won't be able to do this part of it. Yep. So I think I can get into what I want to get into if I go into the docs folder here. I can't get all the pictures up though, but I can at least show you something out of this. I thought I had a PDF stored in this GitHub site too. This makes use of a Kalman filter, so I wasn't going to the read the docs page, never mind. So there it is. So here's the read the docs page, just like I have for Scikit DSP.com. And then there's a bunch of notebook examples, and these are all rendered out into PDFs. So these examples go through a number of things about learning how Kalman filters work that are based on a book that I was using at the time. that I was developing the notes for the tutorial lecture that I did up in Denver. And the author is Kim. So I may have his reference down here. I know I have it somewhere in here. It's maybe not on that page. Probably shouldn't be wasting time on this stuff. The author's name, though, is Kim, and this was the book I chose to teach the class from because it's very simplified. Dr. Plett has been teaching a Kalman filters course this semester. But after going through a bunch of examples with Kalman filter, building up eventually to a extended Kalman filter, and this is the example as it comes together. This is in one of the notebooks that's on the GitHub site. And the TLEs captured from several years back are there. You have to have SGP4 available, installed in your Python. And I think that's about it, except for the rest of the code. So this just talks about a satellite sitting up there. What is the coordinate system? There's different coordinate systems, but the coordinate system that we need to work this problem is ECEF, which is Earth-centered, Earth-fixed. So that's the one that has the Earth in charge of things. Does everything revolve around the Earth, the way we understand orbital mechanics? We revolve around the sun, right? Because that's the biggest body that creates the gravitational field and so on. But for doing satellite work, you can convert to ECEF, and the system that's actually used in space is ECI. The Earth-centered inertial system is what that stands for. But I converted everything to ECEF, and there's transformation algorithms that take you through that. So we have an object that's flying up in space, like a GPS satellite that has an X, Y, and Z coordinate in the ECEF example. So it's going to be in motion relative to the Earth-centered, Earth-fixed system. And if I take a TLE and I want to propagate it, I can use SGP4, and I did those sorts of things behind the scenes in this code base. So I finally come down to having the ability to run the clock, have the satellites in ECEF, and then have what's going on the ground in this east-north-up coordinate system, but then map that out into ECEF as well. And then I can draw a vector between these satellites down to the point on the ground that's also in motion. So I'm going to have a position vector, a radial that's going to connect those points. Both ends of that radial are moving. Does that make sense from physics? Because the ground person is moving some, and the satellite in space is moving, but that's just the nature of how it would work. When you're receiving the GPS satellite signal, you don't have that radial. In the model I've created here, I can create that radial just from all of the data that I have. In the GPS system, we'll see in the project, you only are able to calculate from your measurements, and this is what you do in the project, something called the pseudo range, which is actually a time difference of arrival. Then what happens is the GPS signal contains some low rate data at 50 bits per second, which has the ephemeris data, which is equivalent to the two-line element set. The ephemeris data tells you where that particular satellite is located in the catalog of all the GPS satellites. And that's updated regularly. So that ephemeris information comes down into your GPS, and your GPS makes these time difference of arrival measurements, the pseudo ranges, and it's going to get the pseudo range, the time to propagate from any one of these satellites to the user as a time difference. Then there's a correction factor that has to be applied, and some other background calculations. That stuff's talked about in the project, but I just wanted to show you kind of how this came together. So what the end product would be. If you have, say, the user moving on a trajectory, and this was a trajectory here on the ground, it was like you're running or driving your car. So more likely driving the car, but it could be running, I suppose, too. So I had this track. You start at the green dot, and I go east for 0.2 miles, and then I make a hard left turn, go north, and then I go west, and then I come down south, come back, and then I end at the red dot. It's just an example to say, okay, this is what I'm going to actually be doing, put this into the model, and then form the pseudo ranges and use some other a priori information off to the side and develop this model, this physics model for what's happening. So here's the east-north up coordinate frame sitting on a spot on the Earth, and here's a particular space vehicle sitting up there with its ECEF coordinate frame. This is just an example of where the local frame might be. Just out of curiosity, do you know where the prime meridian sits? Is this making sense to you as our globe? This would be the equator down here, right? Prime meridian goes through what country? England, right?
Greenwich, right?
Yeah. So we're actually over here. We're west longitude. We're not east. So this would be, I don't know, maybe it's the Ukraine. I don't know. I don't know where it is exactly. Maybe it's Russia or something like that. But I just threw it on there as a representative. So I get position for all the satellites. I get velocity. I have clock bias and clock drift, which are things that the other document talks about for all the satellites that I'm tracking. And then that, then you have a state transition matrix, which contains all of the terms for the vehicles that you're tracking. In this case, it's 4. I'm assuming I need at least 4 satellites. I need 4 satellites because I want to be able to get position, X, Y, and Z. And then you have to have a 4th one to remove an uncertainty. And that's talked about in the project document. But I'm just showing you there's some math involved here. There's some covariance matrices which refer to the error model that's involved, and some assumptions that I got from a reference book. And finally, the pseudo range comes in, and this is what the project calculates. This pseudo range is going to be a pseudo range, but it's actually a time measurement until you put c times it. So velocity propagation times time, what's that going to do? If you have meters per second times seconds, you're going to have meters, right? So pseudo range is actually going to be a range in meters. So you need some other math for this extended Kalman filter, this thing called a Jacobian, which is some partials, which involves some geometries. And I'm just showing you there's definitely math in this model. And then finally, what you're able to do is run the simulation. So I create and generate the trajectory and create some test matrices that go into the solution, and then finally I run this function, GPS extended Kalman filter, and it takes in what the user's doing, user position. It's putting in some random noise to represent the fact the measurements are going to have some noise. It's putting in some other attributes that control the quality of the estimates, and then it outputs position converted back to east, north, up. And finally, when the Kalman filter is running, I can look at the errors on the estimated values of X, Y, and Z. And this is the convergence of the filter. It's an adaptive kind of a filtering algorithm. Then I can look at covariances and since you haven't had Kalman filtering, this is just kind of like, what is all of that? Well, it's just saying when you first engage the filter, it has to start tracking, and then some of the variances of elements along the diagonal of the covariance matrix settle, saying that it's pulling in, it's converging. And that's, if you've ever first turned on a GPS, even on your cell phone, when you're, suppose you traveled across the country, got off the airplane, the satellites overhead are not satellites that your phone has ever seen before because your phone was in airplane mode. Picture that, okay? You turn it on and it starts looking for what satellites are up there, what space vehicle numbers are going to be overhead at that moment. It's going to take a little bit of time for it to actually figure that out, find out what satellites it can lock onto, which is your project here, and then finally get the ephemeris data from the 50 bits per second, then work towards getting that solution. So have you ever been wondering why you can't put yourself on the map quickly on your phone? Has anybody ever experienced that? If you, here in town, your phone's in your pocket, it's running, you turn on your mapping to, well, you're right there in the map, right? But what I'm saying is get off an airplane after you've moved and your phone doesn't know what satellites are currently overhead because it hasn't been seeing them. It's got to figure this stuff out. So it kind of fumbles around a little bit. Try that sometime just to prove to yourself that it's not always on. I'll get back to my peeve on instant gratification again. Our systems aren't that perfect. So this was one run done at 5 miles per hour, and you can see it's got a little bit of buzzing, but because it's updating once a millisecond, it's getting another pseudo range. It's working very, very well, and the errors are relatively small. So what I did here is I made it run faster. So I made the user move around the course at a faster speed. You can see that these little arcs are very tiny. And so every time, this is the error, every time I took a curve, it was like, whoops, you changed direction on me, and I wasn't able to figure it out right away. There's more of a transient now because things are happening faster. Does that make sense? Try running really fast and all of a sudden making a right-hand turn. You can't do it, right? Because your body is going to fly off because of the momentum you have in that direction. But at any rate, the algorithm has the same problem. It can't grab it. So it settles a little bit slower, and you can see here at 30 miles an hour, it's pulling in, but it has a little bit of overshoot every time. Is this intriguing, or maybe it's not intriguing, but to me it's, I did all these things because I wanted to do what I thought would be the right way to test this out, and to me this was pretty satisfying. This reference 4 is what Dr. Plett usually teaches his course out of. So that's some background. Any questions? Or you're so young that you just take it all for granted, somebody figured it out. EE's figured this stuff out. We're the ones, in aerospace people, we're the ones that are kind of in charge of this stuff, making it happen. So I'm going to go back over to here so I can write on it. So we just looked at the GitHub. I'm just showing you here as I back up. There's problem number 1 is having to figure out a tracking function, and that one I can't really explain what it is, but this one is probably the hardest one, problem number 1. Problem number 2 is studying code to see that I have a particular system function f of z in a particular area of code. So you have to study this little block of code called the find track close loop, close the tracking loop, and what this code is doing. Why did I put that in here? As an engineer, sometimes you have to look at other people's code and you have to figure out what did they do if they didn't document something. So there's a difference equation running here, and you're just going to verify it. Then in 3 is where you actually do a series of experiments, and you just run the code to get it to happen, and try some different scenarios. It's just pretty much run it. And Kaylee, you started working with it already. The code, it works, right? Okay. I have it up, and I can run the notebook if I so feel like it at any moment here. So now what I want to do is take you back to the beginning and just show you the main blocks that are in here. GPS was started in 1973. When I started in industry at Motorola Government Electronics, the transponders for the Navstar system were built in the same place where I worked down in Scottsdale, Arizona. And they were fielding units when I was there in 1979, I think, is when I started there. Yes, I know I'm old, but that's when that stuff was going on. So what is Navstar? Navstar was the original name that the creators made for what is now known as the Global Positioning System. So Navstar is an acronym: Navigation, Satellite, Timing, and Ranging System. And this is a picture from the internet just showing you that there's nominally 24 satellites up in orbit, and there's 4 different planes, or there's a number of orbital planes. I don't remember how many planes there are in these orbits, but orbital planes means that there's an ellipse, or if you slice through the sphere, it looks elliptical. I believe it's not perfectly circular, but it might be circular, that the satellites sit in. If you remember, months and months ago, Putin over in Russia said that he would start shooting our GPS satellites out of the sky if we did certain things. Anybody remember that? What do you think? It sounds scary, right? Satellites go away. But we have satellites, backup satellites that can be moved into position that are already in orbit. We also can launch more satellites. So that's Star Wars Maximal or something like that, right? I mean, it's our technology. It's just what we've done. You know, decade or centuries ago, it was just having metal for warriors. Now we've advanced, you know, in the way things have to be done for defensive stuff. So the satellites are in an orbit of 20,000 kilometers, 12,000 miles. This makes them MEO, medium Earth orbit, as opposed to LEO. The company I'm working at does LEO satellites for reconnaissance. So those are very low Earth orbit satellites. And then GEO is what we think of for most of the media that we do. And then there's high Earth orbit too. So the orbit is 11 hours and 58 minutes, but that constellation provides a nominal view of 6 at any time from the surface of the Earth. Now, what obscures the ability to see satellites are, what do you think the mountains do? You can't watch a satellite go down to hit the horizon when you've got a mountain range there. If you're in a backpacking like I've been, in between ranges of mountains and hills, you can be obscured such that you cannot find enough satellites to get your position fixed. You might have to climb up higher or something to get everything in view. But nominally, that was the design. It's flying at a certain velocity, about 7,000 miles per hour. So that introduces a Doppler onto the carrier frequency, which is at 1.57542 gigahertz. So that complicates the ability to receive these signals because there's a Doppler on there and it changes. This is the model that you find on the internet, on the Wikipedia site, I think, that just shows you how you can find position relative to the Earth's center. And the user is denoted there. If you have 2 satellites, you can find, you can see that there's 2 intersection points there. Here and here are those spheres. If you have 3 satellites, then you have the intersection point of all 3. But in spite of that, you still have an ambiguity But that ambiguity, turns out, can be resolved, if I'm remembering right, because one of the solutions puts you inside the surface of the Earth, whereas the other one does not. And there's those types of things that come up when you're doing orbital mechanics and things too. So you're thinking about solving this out. It's not a simple closed form solution. It's a numerical solution to solve it out because the measurements have error. If you want to get elevation, though, which takes you beyond just getting you on the surface of the Earth, then you need the fourth satellite to see how far above the surface of the Earth you might be. And that's probably the hardest thing to do. I mean, it's if you're like me with a watch, I used to have a Garmin sports watch that I would go backpacking with. If you want to use it to get altitude with GPS, it's still not very accurate. So most watches that people would use for backpacking would have an altimeter in them. So the altimeter works off of pressure, and then you can get altitude that way, usually more accurately than GPS can. But anybody ever done that before? Know what I'm talking about? The altimeter-based solution. Altimeter changes with temperature and pressure, though, so I don't know. I got into all this stuff doing a lot of backpacking, and carry a topo map. Then you can figure out, if you know where you're at on the map, you know what elevation you're at nominally. So you have alternative means to figure out how high up you are. So we have a vector ECEF, and the length of that vector is what the double bars mean in math. That would be the norm of a vector. So how do we figure out the range on signals between one location and another? We use a code, and there's two types of codes used in GPS. One is the course acquisition code, which is a gold code by its inventor, Gold. And then there's, and that code has a bit rate referred to as a chip rate if it's spread spectrum, which is what this is. So the binary chips or bits are sent at 1.023 megachips per second. The code period is 1023. So that means that in 1 millisecond, one period of the code nominally cycles through because of the design of it. That's why it's 1.023. I'm not the creator of it, but I like the way they did it. It's like it's exactly 1 millisecond to go through one code period. There's 37 gold codes in the family. You have a file in the zip package for this that has all of those gold codes in it. And they're assigned to the space vehicles. And all that stuff you can find on the internet. So how do we know when we have a local code that we can generate aligned with the received code? We have to do a cross correlation. So the cross correlation is an integral, would be the product of code I with code J, and we're going to be integrating over time, and tau is an uncertainty. We don't know the difference in arrival between those two codes. One of those would be the local code, the other one would be the one we're receiving. Another property of the codes is that they're nominally mutually orthogonal. So all of the space vehicles transmit their own unique gold code. When we sit on the ground and we want to look for a particular gold code, we just use that one and cross-correlate all those received signals which are impinging on us, but only one of them is going to show a correlation, the one that matches the one that we're correlating with. And that's how we sift through it. If you remember, an earlier generation of cellular telephony was CDMA, known as Code Division Multiple Access. So that means you can access a different resource using its unique code, and that's what our cell phones still do today if there's a CDMA cell tower that you're trying to talk to. But this idea originated for secure communications a long time ago. It started, I think, during the end of World War II, using spread spectrum, and it's still used for secure communications by the government. Actually, my big project that I'm working on in this company is a spread spectrum project. It moved into the commercial realm, but GPS was around since before the cellular use of spread spectrum. So we pick out using the local code that we're looking for. We don't actually know what's out there until we search around to see if we can get a correlation peak. So the first phase in this is coarse code alignment, and then the second phase is fine tracking. So we have a code coming at us. We don't know its time alignment because our distance is not known to that satellite, and that satellite's in motion on top of it. But we search for a close alignment by moving the code locally relative to the one we're receiving, and then once it gets close enough, then we go into the fine track mode. That's the main focus of this entire project, is the acquisition and tracking of the signal. It's a hugely important thing, and it's DSP, comms, and then the tracking part is related to control systems, but it's also could be viewed as a special type of phase-locked loop, which you learn about in COM 1. And actually, it's called a delay-locked loop. Delay meaning that we're trying to lock onto a delay. We're trying to move the delay of the local code relative to the received code to just track it, and then we can get the pseudo range once we're tracking it. I did not mention that besides the CA code, coarse acquisition, there's called a P code. There's a P code that runs at 10 times as fast, 1 order of magnitude bit rate faster, and that's the precision code that the military gets to use. It has a much longer code period. It's an unknown code period. It's a secret, and then finding the alignment of that is techniques that they have to use for the precision stuff. Why did they build the system this way? Coarse acquisition was a bootstrapping process. Does that surprise you that a complex, high precision system decided it needed a bootstrap? So at first the coarse acquisition, and then if you're doing military application, then you try to acquire and track the precision code. This project has nothing to do with the P code. There's Y codes, and then there's advanced GPS, which is using somewhat different schemes right now, but they still all have steps like this that they have to go through. So I'm not going to say anything more about P code, the higher rate code, just the CA code. So what do we get when the data comes down, encoded onto it with binary modulation is a bit stream of 50 bits per second on top of the CA code, and that brings these bulleted items in: satellite almanac data, what's been going on over a period of time, what's the ephemeris data for the satellite, what's the signal timing data, ionospheric delay data, and satellite health message. All sound kind of like cool things. I don't think our cell phones unravel all of that. They unravel the ephemeris for sure, and probably the almanac data. So we're not simulating with the 50 bits per second data. We're just making some assumptions about things. We're assuming everything's perfect except for the code alignment. So the transmitted signal is the timing waveform across the top. The received code is now delayed by delta t seconds when it hits the receiver, and that's due to the range that it has to travel. What's the velocity of propagation? Just checking, is your brain thinking? It's speed of light in a vacuum approximately, right? So we can relate that to velocity, and if you want to get down into seconds rather than just code chips. So when the code slides past itself, in other words, we create a replica code at the receiver, and it's going to move around to try to align with this received code, and when it aligns with it perfectly, it will be at a correlation peak, and as it's coming into alignment, it rises up from a low cross correlation of approximately 0 rises up to the peak, and then comes back down again as if it were to slide by. So the job of the algorithms in this project are to step the code, say a half a chip, or a smaller amount, depending upon whether you're working problem 1 or problem 3. So nominally in operation you step at half a chip, because that way you can search rapidly. You have to keep testing, and by searching at a half chip interval, what you're allowed to do, I think I have a picture down here. Unfortunately, it's way down here. This is just a zoom in on that correlation peak. As you're sliding through here, by stepping at a half a chip each time, you're hopefully going to get, one value that's at 0, one that starts to rise up, and one that's maybe near the peak. And then as it steps a half chip again, it will get 3 values from 3 different correlators, one that's skewed early by half a chip, one that's skewed late. And then when this situation occurs, like this picture is showing, then the tracking loop sees, oh, the prompt code is correlating near a peak. I'm going to switch to the track mode, and the early and the late signals are used in a feedback control system to keep it tracking on the peak. Does that make sense? If you could change the clock speed, you could just take that peak and you could dial it back and forth and just sit on it. And this is actually showing what that pull-in looks like. Over here, the green one, which was, well, the red one, which is the prompt, it finally crossed over a threshold, and then immediately what happened when the threshold is right here, where it crossed over, it said, we're heading towards the peak, we're pretty close to the peak, we're not actually at it, but it says flip it to track mode, and then it immediately started to pull in. So these two signals are going to pull in, and they're going to be equal to each other when it's settled, and then we're tracking up here with the red one, the prompt, right on the peak. That's kind of the pull in and then track operation. All the code's written for this, of course. So how do we generate the signals in the simulation? I make the assumption that I'm using one of the little radio dongles we use in the comm lab to receive the signal from a patch antenna, and I'm operating at 2.4 mega samples per second. My signal's at 1.023 mega chips per second, so I'm sampling at just a little more than twice the bit rate, which is pretty low down, but it can work. So I simulate the signal at 3 samples per chip, and then I downsample it fractionally to get down to 2.4, and you can create n different signals for n different satellites all in parallel, and then you can create instances of a class that form the tracking for each of the individual channels. Like you're going to track a satellite SV4, SV10, SV18 or something. You're going to set up tracking algorithms and receiver acquisition systems, and then you'd get these pseudo ranges coming out, and you'd also get the data bits out, and they would go to your navigation receiver processor, which would be like your cell phone. I didn't bring down, I should have, I have a little tiny GPS up in my office, it's just a little tiny patch, and it's got an RS-232 on it, so I can just take it and plug it into a laptop with an RS-232 connection, and then watch the data come flying in. It formats the data as ASCII characters, and you can process it into location information. So you end up using, in the code, a function to generate the transmit signal, or the received signal that would be leaving the satellites. You get to put in different parameters, how many chips you're going to simulate, which gold code you're going to use, and These parameters are not really all in use. I'm not putting Doppler on the signal. I may be putting random phase on, but then you resample that from 3 samples per chip down to just 2.4, and then you add noise into it, and all of these signals, if I was to cut through that, are imposing on your receive antenna through space. So the noise that's shown in there is just representing the noise of the receiver front end. It's added to the signal at the top there, but it's done only once. So be very careful when you read my instructions. Read my instructions very carefully. I'll say it forwards and backwards. Only do that once, because you don't want to say the receiver has n noise sources. That's bogus. You've got one receiver, you've got signals coming in from different sources. I just have to attach the noise onto one of the signals. And we can see that in the code here, I guess, too. So this is that function that generates the received signal, and I guess random phase equals true means that I do have random phase applied. So here we have just one signal being generated. There's the 2.4 megachips per second signal. This is the 3 megachips just coming out for test purposes. And this is just looking at the reference code, I believe. So down here, I'm just going to plot what's happening. There's the 3 samples per chip waveform. When it gets resampled, it looks kind of beat up because it's downsampled, and then there's a filter in there to interpolate. But that's the signal that goes into the receiver then. Looks like that. If we look at the spectrum of that, the 3 samples per chip has a clear null at the spreading code rate, which is 1.023. Our signal, because it's only at 2.4 megachips per second, actually has some aliasing because we're not sampling at a high enough rate to avoid some aliasing. But it still is adequate. The most important thing is this main lobe, and the spectrum gets captured, and it can work with it. So carrier to noise ratio is the performance measure, and this is just done in the background for you with an algorithm called complex additive white Gaussian noise. I put the waveform into it, and I'm going to add noise onto it, taking into account the change in chip rate or sampling rate. And so here's an example of creating 2 signals. One is using space vehicle 1, the other one is using space vehicle 5. So these 2 values in here are 2 received signals, and then I add noise on to the first of them, but I don't add noise on to the second one, because remember, I only need to do it once. So when I want to get my test signal, this is the received test signal for 1 and 5 is I take the composite signal R for the first signal, which has noise on it, and just simply add the noise-free copy of signal 5 onto it, S245. That's this guy right in here. So when you have to do more than 2, you have to just generate additional signals like shown here, but you only add noise once, and that's this 3rd line. And then you just keep adding signals on as needed if you're going to generate if you're going to receive, say, 4 different signals or 3 different signals. That's part of problem 3. And here I'm plotting the spectrum at this particular signal to noise ratio, which is 50 minus 60 in terms of SNR, but in C over N0, it's a different number. It's going to be, we're looking for 60 dB, and we have to do this conversion. So this is the SNR. This is the C over N0, I mean, at 50 dB. This blue would be no noise added in, and the green is what the receiver sees when the noise is added. A typical value for a received GPS signal is around 50 dB hertz is what that C over N0 actually is. So what do you notice about that? The signal is what? Buried in noise. That's one of the characteristics of spread spectrum. Make things hard to find. But why does the GPS signal have to be hard to find? That's sort of a more detailed question. The government has regulations on flux density coming from a single signal. And by spreading the signal out, the 50 bits per second signal, if you think of it that way, spreading it out in a wider frequency band makes the flux density lower because it spreads it out more. So that's part of another benefit you get from spread spectrum. But you have to be able to get the spreading code locked and tracked. Otherwise, the signal is just not good. But the signal has some jamming immunity as a result of the spreading. The P code signal has a lot more jamming immunity because it's 10 times faster. Still not good enough though, so that's why we've gone to other advanced GPS stuff, but that's kind of cool. So on the receive side here, the signal comes in. This is the composite signal of multiple satellites. And then we have in this tan shaded box, this represents one instance of a tracking loop receiver. So it's one of many receivers that are implemented. This is just one. This signal can be split to go into another instance. As many instances of receivers as you need would spring off of that. So this is just one instance, the one that I'm just focusing on here. So inside the box, we have at the heart of it our local code generator. So the local code generator is this code lookup table. So it's just stored as a lookup table. It can look up the values from the code that comes in from the data, an ASCII file that's in the zip package. So it can look up the gold code values as zeros and ones, and it converts them to plus and minus 1 values. Those values are pulled out of the lookup table with what's called a code NCO. So it's a numerically controlled oscillator. It's basically the clock source. It's ticking away at the nominal chip rate of the system, all scaled accordingly. So the code NCO, though, has the ability to be driven by an input that can slow down or speed up the clock. Because how are we going to make the local clock and the local spreading code latch on to the received signal? We're going to have to speed it up and slow it down and pull in a tracking loop for that. Now, if you're daydreaming or saying, this is so much stuff, I don't care about any of this stuff, and I'm looking at some of your expressions right now, the system doesn't do anything without this tracking. Is that clear? It's just junk. It's just something radiating on your body that's saying, it doesn't make me feel good, it doesn't make me feel bad. It's just, some RF energy that doesn't do anything. Maybe it adds a fraction of a degree to your temperature, but I don't think so. I think you could still freeze outside on a day like today in front of a lot of RF and you wouldn't notice it. At any rate, the intelligent part is doing the correlation. So here we're going to do that correlation integral is actually being done now as a numerical integral. So we're going to multiply the local code times the received signal. All the signals are composite, but when we multiply by a local code of interest, and these represent early and late waveforms. This will be a half chip early, a half chip late, or whatever value I set, and this will be the prompt code down here, the on-time code. They all run through the same structure, an accumulator which just takes the complex numbers coming out and adds them to the previous value. So it's a very simple low-pass filter operation where I just take these complex numbers, the /2 means it's complex, I take the magnitude squared, add it to the previous one, add it to the previous one, and I'm going to accumulate 1 millisecond of code correlations or multiplications. And remember, 1 millisecond is nominally just one code period. And so the decimate by L is just saying that I'm going to accumulate all of that and just send out one value every millisecond. It's actually a complex sum in here. It's not the magnitude until I take the magnitude over here. So that represents the energy in the early signal. This is the energy in the late signal. Then down below here I have the energy in the prompt signal. The prompt signal is the one initially of focus because we're looking to see that that one's prompt signal correlation is going to cross a threshold. And when it crosses a threshold, code in here is going to say we've detected lock. We're now going to tell the code NCO to shift into its track mode. When it shifts into the track mode, the two signals coming in here get formed by this function, and this is what you explore in problem 1, the forming of the discriminator function. And that discriminator function has an S-curve shape to it. So ultimately, what's most important from a control system standpoint is an error signal, and it's only valid for about plus and minus TC over 2. But we're assuming we're not going to tell it to start tracking until the detector says the prompt signal is high enough. So when it goes to pull in, what comes out of this DLL discriminator, or this math function here, is a waveform that looks like that S-curve shape. In phase-lock loop theory, they call that an S. Can you relate to that? It's not a perfectly formed letter S in our alphabet, but it has an S kind of a shape. The important thing is it crosses through 0 when the error is 0, and then has a positive slope that you can characterize with a certain value that nominally can be used in your control system design. So that the gain of that tracking loop function is its slope, and that can go into the loop filter then, which does a control system function, which you can see down here. The loop filter is what's called a gain plus an accumulator. So this is just a gain constant, and the 1 over 1 minus e to the minus 1 is our good old accumulator from the first day of class. In control systems, it would be called a proportional plus integral type controller. And the loop filter forms mathematically what's called the lead lag type of loop filter. So you have the ability to compensate the system. If you just put an accumulator in there, then it can go unstable. By having that gain constant K1, you can lead correct phase-wise in such a way that you can control the damping. And Kaylee, you're the only one that you're taking controls, right? So you're familiar with those terms. The rest of you, if you haven't done this stuff, don't worry about it. It's just there, though. The K1 is to help make sure that it can stay stable. And the simple model is it's a second-order system. If the damping is kept less than 1, which is what we want, it will have some overshoot, but it pulls in more rapidly. We just don't want the overshoot to be crazy wild, and don't want it to start ringing because it'll never pull in. So you have to be able to control it. In a practical system, there would be a carrier aiding based on Doppler. There'd be another tracking loop out there, which I'm showing on the far left, carrier NCO, but that's not implemented. And those are just other things. Chips per sample is another value that goes into scale for the code NCO. So here we have a fractional number of chips per sample into the NCO. It looks kind of complicated, but imagining replicating that, that's what your cell phone can do. It can track probably 6 or 8, not more than 6, but it can track up to 6 in your cell phone, I'm pretty sure. The receiver can do that because it's all integrated I know my old Garmin GPS can do 6 satellites, and it has a nice little picture of telling you what satellites are in view, what their SV number is. And when I worked this project, that was very helpful, because that way when I was doing my actual experiment, it told me what SV was. I knew SV1 had gold code 5 or something like that, and I could make this thing all work. So that was helpful to me. I've talked through a lot of what's in here, so I'm not really going to repeat that. The big function here, though, is CA track, and it's what does all of this thing in the gray shaded region. So CA search track is the tan box. There is another class inside of it called code NCO, so that's an object also, but that gets instantiated inside the CA search track, or CA track, I guess is what I call it. So here's all of what it does, what its inputs are. The outputs are probably the most important to you, because they're going to be messed with. Occasionally you might change the tracking loop bandwidth for one of the experiments, but it's all defined here. So here would be what a system would look like for just a single satellite. We're going to set C over N0 very high at 100 dB. Generate a signal. Here I'm using gold code 1. Add noise onto that. And I'm also going to put a little bit of delay on it, and that's what these parameters in here allow me to do some delay tweaking. And you can read the README part for that in the notebook. And then put in the additive white Gaussian noise. And the next thing I do here is I say take that signal that comes out, the received signal, send it into an instance of the tracker, CA track, and here I'm generating an instance with these attributes. I'm going to step the replica back 0.05 chips per every millisecond. I could search forward or backwards, it doesn't really matter. It's an uncertainty I have to resolve, so I don't know where in the code I am, and if I'm trying to find in a long code, that's the point I want to go to. What difference does it make whether I go like that, trying to find it and come around again, or whether I go backwards? The important thing is, though, if you've got to search an uncertainty region of 1,000 chips, let's just say you're going to do half a chip per test. That's 2,000 uncertainty cells you have to search over. Assuming equally likely statistics, how many code cells are you going to have to search over? If it's 2,000 individual cells, on average, how many should it be? Just common sense. Should be half, right? Worst case scenario. So that times a millisecond per sample, that's how many milliseconds it's going to take to do your search. It gives you an idea of what the complexity of GPS can be. There's also a probability that it will fail to find it on the first pass. It might be right there in the peak, but it might have bad noise or something and not cross the threshold, in which case then it has to go all the way around again. So there's different strategies for searching. Mine is very simple. Serial search, nothing more. In real systems, they have to do, with long codes, they can't wait for the whole code period, so they have to do more sophisticated types of searches, like a zigzag search, where you start at a particular initial guess and then you start expanding it. It's called the expanding window search. You start going back and forth above what your best guess was. Or maybe the secure aircraft leaves the airport and they've been connected, so they know where the code alignment was when they left the mission base, and then when they fly out and want to keep tracking, they already have an a priori of how to find it. They don't want the enemy to know what it is, though. Does that stuff make sense to you? That's how crazy this is with spread spectrum. But when it was invented, it was like, how are we going to keep the enemy from getting our stuff? So it's sophisticated, not trivial. Cellular telephony solved it different ways with a lot of side information. At any rate, we start tracking it, and here I go ahead and set the lock threshold artificially high at 2,500, And when this thing starts to run, it's going to report how many chips have been processed, what the index is. So it's continuing to search for code alignment. These are the values of K1 and K2 that were programmed in based on other attributes when this instance was created. I don't know why I don't show that in here. But at any rate, it's searching, and I didn't show it all, but it never locks. So what it's going to do, if I plot the early prompt and late accumulator outputs over time, it just shows you this. It shows you that as time rolled on, it did, with the prompt accumulator, it went right over the proper code alignment, but because I set the threshold high, it just kept searching. So it started searching from 0 and 1 millisecond intervals, and early prompt and late are all coming up, sequenced by half a chip. So half a chip, these are increments of a millisecond, but the idea is that it's there. If I lower the threshold on the prompt, which is what I do here, I take it down to 2,000. I'm still going to step the code backwards at only 0.05 chips rather than 0.5 chips in a practical setting, which is problem 3. You see it's going along down here. Well, I'm looking at a bigger picture now. I'm zooming out and I'm seeing 3 correlation peaks. My threshold was at 2,000. I need to lower it so I can get a hit and start tracking it. These things are the side lobes that you get with the gold code. It's not perfectly orthogonal. So here I drop it down to 1,500, and it should find it. So it does find it. It tells you that it goes from search to find track, and then it just continues to follow that along, unless it was to get disrupted by signal being obscured or whatever. But it's able to pull it in. And actually, if you plot the tracking error, which is another variable that comes out in the data structure, you can see that it initially pulled in with a large error, and then it overshot and then settles. I generally try to get a damping factor of 0.707 in a second order tracking loop. What about your control systems? Does 0.707 show up ever? It's kind of a trade-off between the best performance in noise, the most rapid settling time, and not having an excessive amount of overshoot. The pseudo range, meanwhile, is also coming out, and until it gets initial lock, it can't even display a pseudo range. It will be 0, but once it gets a lock, then it starts settling in with the tracking loop, and out in here is where the pseudo range is making sense and could be used for the nav solution, which is what we were looking at on a GPS helper. If you reduce the signal to noise ratio, in this case I take it down to just 60 dB C over N0, then you can see that the correlator outputs have noise on them, but still they're able to pull in, they're able to cross the threshold, and there's noise on the tracking loop as well, and there's some noise in the pseudo range. So what do you think that noise translates into on the pseudo range for you, the user? It's going to be your accuracy, right? You're not going to be at a fixed point. You're going to kind of be in a uncertainty region in terms of where your solution comes out. And then there's other factors that I'm not incorporating into this. This is just due to the additive noise. So I know I've spent a huge amount of time on this, but this is a really fun project, and you don't have to write hardly any code. I'm going to let you now take off on your own and play with it. It's all over here in this notebook. Everything just goes step by step from here. These are all the things. There's some test data that was left over inside of here, but it's mostly like most of the sample notebooks you've seen from me before. This is your playground, right? Question?
Yeah, I was curious, is the noise additive
No, you have to add that in. So what you have to do manually, you have to do like what I showed way up in here. Good question, because this is something that I don't like to have to grade through and see that it got hosed up one way or another. So here I generated 2 received signals. I had it automatically scale the noise according to the signal 2.4 megasamples per second, and that 1 means SV1. And then I generated a noise-free version at SV5, but I just add the SV5 signal on right down here. To it.
A new signal.
Yeah.
But it just includes the noise.
Yeah. Because the noise that's on this first signal is already the noise for any other waveform that you get, because it's the same receiver front end. So you just add more in. Does it make sense? Okay. The rest of you, it's forcing you to go read to understand what's going on, but just think back to this block diagram up here. This kind of explains what it is, and I talk about it in here. This is your receiver. This is your antenna. So think of this as being your antenna. All these signals are coming at it. That instance of white Gaussian noise just represents the electronics sitting there at the antenna. The low noise amplifier sets the noise floor, and that happens regardless of how many signals you receive. All these other signals just superimpose in space as they travel from the satellites to you on the ground. So it's not fair to put more copies of noise in, because the noise gets generated actually represents what the receiver is doing onto itself. Good? If I brought down my little antenna, maybe I'll run up and get it. It'll make it's a little teeny patch. It's not as small as what's in your cell phone, but it'll maybe give you an idea of what's inside your cell phone actually. Okay, I think we should take the break right now before I start rolling into a chapter. This is a nice hands-on example, though. Is it the best hands-on example? I don't know. I got somebody that picked up the one from a year that I used last year, a company in California that I still haven't talked to them yet. They wanted me to work for them solving a problem based on that project, but that's fine. This is the more important stuff. I didn't want to do that. I wasn't supposed to do that. I was supposed to unpause it. So what's it going to do right now? I was supposed to just hit run, so I wonder if I have 2 threads running. No, maybe it did the right thing. I sure hope so. I can't stop it now, though. I hope I didn't trash something. I get excited, and I should have not clicked that. I knew something didn't seem right to me. I was supposed to right-click over this, and I was supposed to go resume recording. I think that's what it did. At any rate, I'm going to now dial off of this. If I have 2 different recordings when I get done, I'll just have to merge them together. So now I'm going to go to chapter 6, and before I do that, I'll just take a really quick look over here at what are the problems that I gave you for this. There's 5 problems. 1 is a bonus problem. And the 5th one is talked about in a notebook that I'll be showing you a little bit later as we squeeze down for time. I do have the due dates for these problems staged off, though. So it's not due next Wednesday, it's due on the 9th, and then the one on the FFT is due on Monday, just so I can slide them off a little bit in time so you don't feel quite as cramped. You can turn them in whenever you're ready, though. These are going to be much faster. I know you don't believe me, but it's true. Number 5 is a fun one, though, and it's worked out of a Jupyter notebook. I don't give you a sample notebook for it because the examples are in. It's kind of already started in this sample notebook right here. I haven't run this one yet, so there aren't any pictures in here, but we'll see it. I guess I'll run my kickoff cell, and then I'll be able to start running stuff. I'll run a few of the cells through here. So that problem number 5, will be out of this section right here, fixed point. And while I'm flying by this stuff, I have another PSD function that I've never showed you that is related to the PSD function that's part of matplotlib. But I have a different version of it where I can get access to the spectrum and the frequency vector. And I just use that in here for convenience. And that way we don't have to worry about the simple spectrum analyzer function anyway. But we'll get into this momentarily. So structures for systems. This is kind of like the network analysis side of things for DSP. Not as in resistor, capacitor, inductor, but in signal flow graphs, signal block diagrams. So the fact of the matter is, for a given system, there's many possible computational structures to consider. If we're always considering with perfect infinite precision math and perfectly linear, yeah, there's probably only one math model that makes sense. It's the difference equation that we saw long ago, right? Or LCCDE. But there's different ways of implementing that difference equation. And that actually bears itself out in problem 2 of the project, where you're looking at that simple loop filter, how I implemented that in code. You'll be able to understand it once you stare at the code and fumble around with it a little bit. I say fumble around because it's really easy when you write filter code to maybe not make things as obvious as they could be, but they work. And that's, maybe none of you think that that's the case with you. You'll never do that in your life. Well, guess what? I've been staring at a lot of your code for a lot of days now, and people do things that are hard for me to follow because it's your work, it's not my work. Everybody thinks differently. So you will have to look at somebody else's code. In my job, I've got a guy a junior engineer that I'm working with, and I'm mentoring him a lot, so he's expecting me to do wonderful things, and I'm expecting him to learn quickly, and so far he impresses me a fair amount. He's very high energy and wants to learn. So right now, what are the major building blocks to implement a system? The fundamental building blocks are being able to add 2 sequences and being able to multiply a sequence by a constant A, and being able to put in a sequence delay. Say a z to the minus 1 is our fundamental one sample delay, and frequently in the block diagrams we'll be seeing that's generally what's done, because that would be a computational unit, that would be a register somewhere. So if you put a z to the minus 200 in there, you're mathematically saying, wow, I've got 200 registers that I'm using to save something to make a delay line. You don't want to do that when you're studying topology necessarily. You want to account for each and every delay. So this is our rational system function, h of z. The book does something here that it seems kind of unfortunate, but it's just is done for convenience in this chapter. And it's that minus sign right there. They rearrange the math so they put a minus sign, which means all the AK coefficients now have a sign flip on them. In working the homework problems for this chapter, you're going to have to think about that when you work the final exam, which will have some problems from this chapter and earlier material. You're going to have to be able to track that out. It's going to be really easy for you to make this sign error unless you're kind of at the top of your game in terms of thinking. Why do they put the minus sign in there? It's because they want to be able to do this. They want to be able to rearrange the difference equation so that both terms on the right-hand side have plus signs on them. So now what we've done effectively is there's a minus sign that's inside each of those coefficients because of what was talked about right up here. Still though, when you're using Python or MATLAB or Julia, all of the difference equation functions work just like they always did. The A vector or A array is the same, so the minus sign is in full view. This is just done here for the topology standpoint, and it's primarily for that blue boxed equation there, so that we can say that it's a linear combination of the feedbacks and the feed forwards, and there's no minus signs dangling around because they're now inside. So this is the direct form structure that comes from that blue boxed equation. You just simply say, I form the output by having this box right here be the feed forwards, and then this other box are the feedbacks. And that's what we have here. So this is the way it's always drawn when you're talking about this structure, direct form 1. Direct form 1 just says form a linear combination of past and present inputs, and then cascade that with linear combination of past outputs wrapped around and fed back in again. So this is called direct form 1. It's the simplest of the forms. It's the standard or the classical form. I didn't come up with the name direct form, but the direct form idea is just saying mathematically I directly implement what's in the math. And you might say, well, maybe I do this first and then maybe I do that second. That's another topology. The standard direct form 1 does the feed forwards first and the feedback second. So the block diagram can be a visual aid, can reference computational complexity, such as that required in VLSI design or Verilog or something of that sort. If you go look at this in the very first homework problem, which is text problem 6.5, I'm just going to hold this up to the light. You can see some colored boxes there, right? It's a direct form structure, and it just asks you about the complexity. So I think it's in part C. How many real multiplications and additions are required? And then part D is, can the number of delay elements be reduced with a different structure? Good question, right? So right now, when you look at the direct form 1, we see, okay, these are all the additions clearly defined. There's 6, well, there's not 6. There's 0 up to m minus 1, so there's m right in here. There are n minus 1 additions. Well, there's n additions here. There's m plus 1 additions in here. No, that's right. I got that wrong. There's n and m. Never mind. I can't add right now. In the number of delay elements, you've got some on the feed-forward side, some on the feedback side. And then, of course, every place you have the branch with the coefficient, that's a multiply. So I've already said that m plus 1 delayed variables must be provided, storage, and then we have m plus 1 plus n coefficients. So that's the burden. I'm going to revisit this again once we go to an alternate form called the signal flow graph form. So the block diagram can be looked at as the cascade of the feed forwards and the feedbacks, and that's these two equations. So I've already alluded to the fact that if you switch to the z domain, for each of those difference equations. One would be h1 of z, the other one would be h2 of z. But in our linear systems modeling, we know that if we have h1 of z times h2 of z, we can change the order. We could do 2 first and 1 second. So an equivalent block diagram would be to reorder, do the feedbacks first and the feed forward second. So now what we've got is the feedbacks on the left side and the feed forwards on the right. And what I always think about when I see this is that is the backbone of our block diagram. It's like we have these delay elements in the block diagram, and that would be like two algorithms sitting back to back. So the vertebrae are touching, and they're sharing the same vertebrae. I mean, this is maybe taking things to extreme. It's not like it's a human or an animal, but it's just a block diagram. But so they could share that same delay element, and lo and behold, we get direct form 2 by just changing the order so that the delay blocks can be shared, and that reduces the number of delay registers that are required. It's now the maximum of m and n that you have to have. Still the same number of multiplies, still the same number of adds, but you reduce the amount of storage. Now, why do we care about this? Well, let's think about this just a little bit. If this algorithm was run and this algorithm over here were both run on a fixed point computing algorithm, every time we do a multiply, we'd have fixed point coefficient number times a fixed point signal. And then if we're playing the game a certain way, maybe we truncate the number or round the number back. Suppose we had 16 bits in the coefficient, 16 bits in the sequence number, so we would multiply 16 bit by 16 bit, we'd have 32 bits, and then we could shift that right, and we would have 16 bits back again. Or what is also talked about in topologies is right at this point right in here, maybe we keep it double wide. We have a register, an accumulation register, both here and here, that's double wide at 32 bits. So we don't take things back until we get out over here. Finally, maybe probably not right there actually either. Well, yeah, probably right here. Exactly, I drew this right the first time. Right at that point, we could quantize the whole accumulator back to 16 bits. There's different ways of doing it though, and that's some of the stuff we'll talk about here in the notes and then in Python. Is that kind of making sense topology-wise? Think of microcontrollers and think of registers and things like that. Those of you who are taking the lab have a huge advantage. What have you been doing in the lab all semester? Keep it as float, right? And don't convert it back to fixed point until you finally send it back out again. But another way would be thinking that you're going to do things in fixed point, but you're going to maybe use 32-bit accumulators inside when you get your 16-bit numbers, and then 16-bit of coefficients, let's say, stored as well. And then you could keep one big register to finally take it back down at the end. Does that make sense? I mean, if you've got that luxury already, just do it. But then the big thing here is that when you do the feed forwards first and the feedback second, there's different quantization that's going to be happening. Even with 32-bit registers, there might be some rounding that's going to happen. Well, it won't be any rounding there, so there's going to act perfect. But if you're going to quantize back after you do each coefficient multiplied, then you're going to have a different impact between these two topologies. The book has little examples which I find to be somewhat good and somewhat not good, but here's just comparing direct form 1 and direct form 2. This example is a good one to point out the sign change business. The fact that that coefficient is minus 1.25 means that it becomes plus 1.25 here, and then the fact that this one has got to have a minus sign and then another minus sign for the coefficient itself to make it be consistent with the change in the model. This one has to have the minus sign shown in the block diagram. Now maybe I've confused you a whole lot with that. Let me know if you're following it or not following it. Inherently we have 1 minus a bunch of stuff, so if it's minus already, then it gets to go right in the block diagram as plus 1.25. If it is plus, then we have to pull a minus sign out, and then to compensate we have to have the minus sign next to the 0.8 in the block diagram. And that same thing is happening whether it's direct form 1 or whether it's direct form 2. The feed forwards don't change at all. They're always going to be as written, plus 3 in this case. Good? Okay, the next thing the book does is decides to go down the path of signal flow graphs. And signal flow graphs is just a streamlined block diagram. It goes into the idea of graph theory, which is something that maybe comes up in control systems. It could come up in microwave networks. It comes up in circuit theory, most certainly. Why did I learn about graph theory? Well, when I was in graduate school at Michigan Tech for my master's degree, my advisor said there's 2 courses offered from ECE this semester, one I'm teaching, one a circuits professor is teaching on graph theory. And I said, why am I taking graph theory? Oh, it's the only course available. So I had a course on graph theory. It was interesting though. I mean, if throughout your life there's sometimes that you do things and you say, I'm going to actually learn something out of this, and I eventually accepted it all. But that was pretty abstract. I can't say I remember a whole lot about it. Cut sets and other graph theory ideas, which the math department probably talks about too. But still, this signal flow graphs are a form of graph theory, but not, in my mind, we don't look at them in such a complex fashion. So you just simply streamline it. You have a node that's a source node, and a node is always literally a little circle, and branches can leave that at will and go off in any direction that you want them to go off into. If you have a sink node, you again have a node that's a circle but branches enter. So the difference between source and sink is just whether or not the nodes have exits or entries. Exits, no problem. You can tap as many times as you want to in the math. There's no loading of the circuit like there would be in an electrical circuit. In logic family, you have fan out. Remember all these things? These are abstract math ideas. So as many branches can emanate from a source node as you want, and as many nodes can come into a sink node. The sink node just has inherent in it is that there's always addition. Whatever is arriving at a sink node is just being added together. And then you have branches, and branches perform linear transformation. So you always have an arrow on it. So this would be called a directed graph, meaning that it has a signal flow direction. Unlike in a circuit theory scenario, if you draw a schematic, current can flow either direction. If you're talking about control systems and microwave circuits, you have to be distinct about it. So, believe it or not, signal flow graphs are used in microwave network theory as well. And there, what they do to make it be a directed graph, like we're talking about here, is they have the incident wave is the feed forward wave, and then what leaves the port of a device is a separate signal, which is the reflected wave. So if you've been taking transmission line theory stuff and taking that stuff and sucking it up into your brain, you can manage that in microwave circuits by just tracking what's incident and what's reflected. And it works, because I've taught that class and it's really cool the way it works there as well. So here is an abstraction then, just showing you a directed graph that has nodes that are sinks and sources. What's a little bit complicated about this is that node right there has got, you know, 2 branches going in, or 3 branches going in, and 1 coming out. So you just have to have 3 additions there and 1 exiting. The words kind of talk about it. If you want to have a branch that has a delay of 1 sample, you just put a z to the minus 1 in front of it. So if this is our first order system block diagram, we can just easily move that to a signal flow graph to look like this. The best thing to do with a signal flow graph is to just label the nodes with numbers, integers like 1, 2, 3, 4, 0, and 5. On the exams coming up, final exam, I'm not going to be able to control what you do in the homework, but on the exam I'll probably give you, if I give you a signal flow graph and ask you to tell me what it does, I'm going to put numbers on there. Why? So when you write your equations out, you won't be, every paper is something different and crazy that I don't understand. So I'm going to give you numbers and want you to follow that. And if you have a signal flow graph, suppose we take away h of z, take away the block diagram, we just have this. We're given a signal flow graph. It's an abstraction now, and how do we get the system function from that? So what we have to do is go inside and start writing equations. So you can write difference equations at different points. So W1 is, you know, this guy right here. So what is W1? You can see it's taking 2 inputs. It's taking X and A times W4. So you can just enumerate all your equations. This should seem a little bit like network theory, right? Nodal analysis, let's say. Let me just ask the question, which is the favorite of yours when you're doing circuit analysis? Which do you tend to relate to better, mesh or node? I'm just curious if you can think back in time. I happen to be a fan of nodes myself. I like node voltages, but the fact of the matter is it doesn't always get you where you want to go. But if it is nodal analysis, that's what we're doing right here, except we don't have to worry about Kirchhoff's laws taking effect at each node. But still, it's kind of similar. So we have all these equations. How are we going to get, let's say our desire is to find out how the input arrives to the output just from the system of equations. So you can start trying to simplify the equations, which is what I'm doing here. I'm saying W1, W2 is W1, and it's that. And then I start simplifying, and as soon as I start simplifying, something ugly starts to happen. You know, I get W4, I say, oh, that's cool, I'll put that in there for W4, and as soon as I do that, now I have a delay in there. And then I go down and write y of n and break it out, and it has W2 of n minus 1 in it, and you kind of start to get balled up with what you're going to do when you make that substitution. So the big and most important thing is when you run into that, you just switch to the z domain. You take everything to the z domain using the delay operator, and you can use your algebra very conveniently, whereas when you have the difference equations, you can't necessarily make substitutions because you have delayed and undelayed copies, and you find the math is just like, I can't do this, I can't think this through in my head. It's not simple enough. So when you go to the z domain, though, you can rewrite the equations by just using the delay theorem and keeping it in terms of your variables, and then strive to find out a representation for y of z from the 3 z domain equations up above, and then just be able to write y of z over x of z, or identify the difference equation, however you want to do it. In this case, we've got the system function back again that we started with, which is right here. But if you wanted to get back to the difference equation for that topology, this would also be true. This does not mean it's implemented that way. It just says this is what it's equivalent to. So usually on the final exam, I'll have one problem that looks kind of bizarre looking. just sort of a general network. And if you think back to circuit theory, you say, yeah, networks problems were just drawn on a flat sheet of paper. Did you ever make something like a resistor cube or something like that? I used to teach this electronics for anybody on the whole campus. So one of the things we did is we made resistor cubes, and then they had to solder. They had to learn how to solder. So they made a resistor cube, which is a three-dimensional configuration of resistors, and then put a connection on 2 points and measure the resistance with their analog discovery, and then look up on the internet, how do you find the solution for the resistance? Different than this problem, but what I'm getting at is when you have a flat network, it might not be as discernible as if you could take something and make it three-dimensional and kind of spin it around and look at it. I always found that to be hard, and what did I have to do when I was in industry? I had to take, since I was a board level designer, I had to draw schematics for everything that I created, and I had to turn the schematic into the drafting person that would do my board layout for me. So requires just drawing a flat representation. This is a cute, flat looking representation, but it maybe doesn't seem very appealing. It doesn't look like a direct form 1, it doesn't look like a direct form 2. It's actually what's called a lattice structure. And in some instances, the lattice structures can be useful for modeling the vocal tract. And the vocal tract, by the way, is modeled as a tube model with different diameters tubes from this part of our throat coming up through different aperture tubes and then coming out through our mouth. So that's an acoustical tube model that is like a transmission line model of different impedance lines. So I'm not saying this is exactly that, but the lattice structure can be related to an acoustical tube model for speech in a human. But maybe it's a pipe organ, maybe it's some other device. I don't know. At any rate, to analyze this guy, you have to just jump into it and figure out what's going on. So I numbered the nodes, wrote the equation, switched to the Z domain, beat on it enough so I could solve it out, and finally, in the end, this is a little bit tortuous, and I grant you, when you take a problem like this, if you start the right way, you will get there and be so happy. If you kind of take a wrong turn, you can turn yourself into a bigger mess. I can't predict that because everybody's going to be different. But in the end, it finally simplifies down to being something pretty straightforward. It simplifies down to what? It looks a little bit like an all-pass filter. As a matter of fact, when you get finally down to it, it is an all-pass filter. So this is just an alternate form of an all-pass filter to build a single section of all-pass filter in this form. Why would anybody want to do that? Well, what's cool about it is an all-pass filter requires a multiplication in the numerator and denominator to create the all-pass. So you have to have that, and maybe you actually have to have 1 over alpha if you actually want to rearrange it slightly. So what's cool about this lattice structure is that there's only one multiply in there. Could you think that up? No, I mean, it's not something that's on my mind, but I find it intriguing. The minus sign is not really a multiply, it's just a sign change in bits. There are quite a few nodes in there, so there's a number of additions that are going on, but there's only one multiplication and one delayed register. Interesting. Jack is not here. Jack is kind of an eccentric thinker about things. Remember, he said at the beginning he likes coding theory, and he says that's all he wants to do. I hope he eventually mellows out and says, I'm going to do more than that as an engineer, but I don't think he would mind me saying that because he's been pretty vocal about that. Hopefully he'll see this and say, wow, this is really interesting. So when you watch this, Jack, assuming you will, you'll find this intriguing. The topology, just like codes, can be very interesting to study. So this is what the direct form 2 would look like for that all-pass filter. See, it does have the 2 multiplies in it, but just 1 delay element. Okay, so now, as the time ticks on down, we've studied the 2 basic topologies, direct form 1, direct form 2. Now we go into some other systems. So for IIR systems that have numerator and denominators, people tend to get really excited about coming up with alternatives. They want to consider things like number of constant multipliers, number of storage registers, and then if it's VLSI, chip area, modularity, data transfer. If it's multiprocessor implementations for things that have to run crazily fast, how do you partition an algorithm, and how do you communicate between the processors? I'm not going to answer any of this. I'm just going to say these are all factors that sometime in your life you're probably going to be running into somebody that says it's got to run really, really fast. We want it to be fast and efficient. Or this is our specific hardware. How can you map these requirements onto this architecture to get the most bang for our buck out of it? So these could be factors and other things. This came off of an article that I was reading. Coefficient quantization, product quantization. And in the end, this is the startling thing. When I was young and in school, it was always getting the minimum number of multipliers because that was considered to be the most complicated things. But nowadays, reducing to the minimum number of multipliers and delay elements may not be the least sensitive to finite precision arithmetic. So just trying to minimize the amount of lifting you have to do, multipliers and shifting and delay elements, if that leads to a bad performance because it's very sensitive to finite precision, then you may have to go back to the drawing board again and say, wait a minute, we can't do that. We have to do something else. So this is just synopsis. Direct form 1 looks like this. Its requirements on the left. Direct form 2 looks like this. Its requirements on the left. This is now in the signal flow graph form. There's some more examples in here. I'm going to skip over these. They're actually kind of silly examples that I took from the book. You'll have some more interesting things to look at in the homework. Instead, I'm just going to jump right into the cascade form. The cascade form says maybe we don't want to make a giant polynomial of feedbacks and feed forwards. Instead, we'd like to break it down into just first and second order polynomials. The advantage being that you're less sensitive to finite precision effects. So you break your h of z down into a ratio of first degree polynomials and then a ratio of second degree polynomials when you multiply those out. And you always want to do it such that your coefficients are real. You would not take a second degree polynomial that has complex roots and factor it into 2 first degrees with complex coefficients. That would be like insanely crazy because now you'd have a coefficient that's complex. No, you keep it as a quadratic. So fundamentally, it says that you try to work with biquadratic sections, a ratio of biquadratic sections. If you have isolated real roots, you could bring those together in a quadratic, which is just fine, but you get down to second order sections, and that's what people mean by cascade of biquads, cascade of biquadratic, and bi meaning top and bottom, quadratic. The ordering of the biquads can be done in an optimal way. MATLAB's toolbox does it one way. Python's gives you a couple different options. MATLAB has very extensive tools for modeling things like this, but Python's is pretty adequate by my way of thinking. And I'll say something about that if we get a chance at the very end. So you would have a cascade of biquadratic sections. Each one would be a second order direct form 2 typically, and this is what it would look like then. You have to run through multiple biquad sections to generate a second order design. You can normalize things differently so you have less multiplies if you want to, and that's going going to bring a coefficient out to the front, but it's saving you a multiply on the inside when you do that, because it saves you that additional operation that you're going to have on the inside of each biquad. But that's not always a good thing to do, because then you lose what they call stage-by-stage gain scaling. You might not be able to control the overflow in an individual biquad section as well as if you put a little trim pot, you might think of, a little tweak value in there to make sure I don't locally have an overflow. But maybe it's great for floating point. I tend to not do that. In the code you've been working with in the lab for the cascade of second order sections, I just use all the coefficients. So again, this is kind of a silly example where they take a second order section and break it into two first order sections. I put it in my notes because it's in the book, but actually no one would ever do that. They would just go as a second order section. There's a fourth type, the parallel form, which you would get by partial fraction expansion. That would be constants with delay, first order, and then second order, all in parallel. And that is, I think I have the picture of that over here. Yeah, this would be what it would look like. This is what the topology would look like. Everything's broken out in parallel rather than in cascade. I don't see anybody that uses this, but it's in all the textbooks, so for completeness, I referred to it. I'm not going to have you do a parallel structure problem, though. I'm mostly interested direct form 1, direct form 2, and cascade, and questions relating to that. So there is an example. I'm not going to look at that. Feedback loops, this is kind of a silly thing, but it just says when you're looking at signal flow graphs, you can actually create something that's called non-computable. So in this situation, we're computable because we have that delay register. So in order to get the output from the input, we just can follow this around. This does lead to the fact, though, that you've got a circulation going around in here. And that circulation means if that coefficient A was to get too close to unity in magnitude, it could cause the system to go unstable. You'd say, I understand that because that would be a pole on the unit circle. But just in terms of round-off errors, it could be a problem. Whenever you have feedback, you always have something circulating around. But that's not to say it might not be an FIR system. Here's an example of a flow graph that looks like it must be recursive because you see a feedback path. But if you write this flow graph out, you see that those two guys cancel, and it's just simply a first order feed-forward system. Would anybody do that on purpose? Probably not, but maybe one person is designing one part of a system, another person another part, and they never looked at what they were doing, and one was undoing what the other person did, or something strange like that. I don't know, this is, again, things I've read about. Then a third consideration is the non-computable loop. You look at this, and you say, how can I compute this? There's no delay in here, so I'm going to be sitting right here, and I need to have this value so I can move forward to the output, but I have to have A times the value over here, and I can't get there until I get that value in red. So this is called non-computable. If you just write that out, though, mathematically, you'd say, oh, I can just do that, and then just say y is x over 1 minus a. So it's what MATLAB Simulink program calls an algebraic loop. And MATLAB Simulink is a block diagram tool that they have. And if you do that by accident, MATLAB Simulink compiler will stop and say, I found an algebraic loop, I'm solving the problem for you, and it'll carry on from there because it's helpful at determining that. If you're doing a complicated control system where you've got a bunch of things going on, it will identify the non-computable loops. So as a general rule, though, a delay element is needed to ensure computability. So we've had direct form 1, direct form 2, cascade are the three I'm most interested in, and then we get transposed signal flow graph. So any network that we've thought about so far can be rewritten using a property of transposition, also known as flow graph reversal. Next week we'll see in the FFT algorithm you can do the same thing when that's realized through a SFG model. So if this is our network, we can transpose the network by just simply doing the steps talked about here. Reverse all branch directions. Sync nodes become source nodes, and source nodes become sync nodes. So this is what it would look like. Going from the top picture down to the bottom, I just make output the input, input the output, and then every arrow I just reverse, and that becomes a transposed signal flow graph. I'm not giving you the proof, but the fact of the matter is the network transfer function does not change under transposition. Normally what we do, though, on this lower one, we'd lift it off the page and flip it over, right? And that's what you'd have to do. If I said in a problem, find the network transposition of this signal flow graph, it'd probably be best to draw it from left to right, since that's how we read in this country. So that would look like this. So the net result for this first order system, you can just see that the multiplication and the delay are now reversed. But if you go up to, say, a direct form 2 biquadratic section and do this flipping, you can see what it has done is it's meaning that direct form 2 had the feedbacks first and the feed forward second. Now under transposition, feed forwards are again first in the flow graph, feedbacks are second, and the direction of the flow on the delay elements is now going up rather than going down. This happens to be what Python's L-filter likes to use and what MATLAB's filter function likes to use. The transposed direct form 2 seemingly is the favorite algorithm used by our numerical tools, just for computation purposes. Sound good? This is kind of just trivia stuff, right? You're not seeing a whole lot of stuff you can do with your hands on the page with this, but there's a few things you can do. Direct form structures don't have the feedback, so a direct form FIR structure just looks like that. A transposed direct form FIR structure just reverses everything. Both are equivalent. This is the one we tend to see the most often. This is also known as a transversal filter or tapped delay line filter. A tapped delay line would be an actual analog transmission line structure with transmission line segments and taps coming off of them. But this is the DSP equivalent of that, a tapped delay line filter. So an FIR filter is sometimes called a transversal filter. This is less convenient, but it just shows you that if you run it backwards, everything taps off at the input, and then the delays are imparted after the filter coefficient weights are put on there. I don't really have one advantaged over the other example in mind, but linear phase FIR can be handled by using symmetry, so you can reduce the number of multiplies. We can think of if the filter coefficients have an even symmetry, then we can just fold the filter around and have the points at each end get the same coefficient and then move into the center like is shown here. So if it's a center tap all by itself, then it just gets the coefficient applied to it rather than summing together two outputs. If you have the other form, then you can, well, for type 2 and type 4, then you can do this topology. where you don't have a center tap, you just simply have a delay and come down to wrap around with it. When I was spending time teaching at Ford Microelectronics, one of the things they asked me about for their big FIR filter that they use to process the accelerometer data, they were implementing it in VLSI, and it's a very large filter. I made this suggestion to them that they use this type of a topology to reduce the number of multiplies by about half. I don't know if they did it or not, but remember we talked about that one day, how it's a very particular design. It's a proprietary design. It's the one that decides when the airbag has to blow. I don't know if I felt honored. I thought they were going to ask me something really hard, and I said, this is the only thing I can tell you if it's a symmetrical filter. But maybe their filter is not symmetrical. They wouldn't talk about it because it's a secret. Makes sense, though, doesn't it? Every automaker, I don't think the National Transportation Safety Board has a standard filter. It seems like they should. I don't know. What do you think?
I think that if a company publishes safety designs like that in the open, and anybody finds wrong with it, then I think it retroactively would open themselves up to a lot of lawsuits. That's probably the reason. I think it also probably keeps like NTSB from wanting to get into that. That's my guess.
Okay, the rest of these are some examples. We then have some finite precision stuff at the end. There's a lot of detail on that, but I'm not holding you responsible. There's one bonus problem on it that you could take a look at, so I don't have time to go through really any of this. What I do have time to go through, and I almost can't get away with it, but I have a minute. I'm going to look at a little bit in here. I do have an IIR design up above, and I'm going to use cascade of second order section coefficient modeling that Python does, and I've incorporated that into this package, IIR Design Helper. And these are the cascade of second order section coefficients, but let's just concentrate briefly on FIR. So I'll load in FIR Design Helper, which you've used. This is the quantizer, simple quant, running in overflow mode. So when it reaches the limit here, it's going to overflow. I'm now going to do a particular design. I'm going to note what the maximum coefficient is. I talk about this in the homework problem number 5. If the maximum coefficient is 0.33, should I set my quantizer value at 1, or can I set it at 1/2? I mean, just think about, if I'm not going to go over 1/2, it seems like I could get another bit out of this. I don't do that in here. I just quantize with the precision at 1. And then I'm going to do a frequency response compare of the quantized and unquantized filter right here. But I guess the question would be, and we'll do it right now since it's so easy to do, when I quantize to 14 bits, you can see that I'm definitely getting some impairment in the stop band. That's what these little ripples are. And my stop band is down 70 dB. What would happen, though, if I did this and then in order to keep the gain the same, I can just apply the 2 afterwards? Does that make sense? I don't even think I have to do the 2, though. Actually, I don't have to do that because I know the maximum value is 0.33, so I shouldn't have a problem. What I'm going to be able to do is distribute my 14-bit precision over a better dynamic range than if I don't do it. So let's just see what happens. It got better, right? Does that make sense? You get to think about this in the homework problem. It's kind of cool, though, right? It's because I don't need all that dynamic range and that coefficient, so I can get more bits spread where they matter. If I had to have a number, if I had to put a quantization level above 1/2 and I never used it for my coefficient, it's kind of like I'm putting 1 bit. 1 bit's not being exercised. That's what you can think about. Then I build up a complete quantization noise and digital filters model. I don't have time to go through that right now, but There's not really much in this notebook, but this part I just went through relates to problem 5. So you're going to have to just lift that out of here, this example, and then you use that when you do that particular problem. The problem is just like that. It'll be done really fast. But you'll be able to play with what we've been talking about with quantization now thrown in there. And you might want to look at this. I've wanted to explore this more if I ever had time. I modified it some last night, but I didn't do a lot with it. I'm doing a quantizer after I accumulate everything like I was suggesting earlier today. And then I can have an input bit precision of something and an interior calculation precision bit width, and then I can take it out. If the bit width at the output is less than the working precision, I will quantize the output as I take it back out again. I haven't played with it too much though. It does seem to work. I know we're out of time, but I'll just run a little picture right here. If it will do it. I didn't run this, I don't think. There we go. So I have something turned off in here. I have the output turned off. Okay, the blue is without quantization, and then the orange is with the full quantization model on an FIR filter. And you see we do have a noise floor again, and that's kind of like the noise floor you saw on the exam problem too. It's a similar kind of thing. We could control the bit width into here and have different factors. This is the input bit width. Well, what is it? B is the input, Bx is the input, B is the working precision inside, and By is the output. So I could mess around with those values. I don't want to take our time from the other class, but we'll see you next week when we'll be jumping over into the FFT. Another very useful tool. We won't get to spend a lot of time on it because I'm also going to incorporate a review for the final into next week as well. So now I get to stop this